Okay, so last time we started looking at encryption technique for as a tool for network security. So I said in a broad sense there could be two type of encryption techniques. So symmetric encryption and asymmetric encryption. So the main difference between the two is in symmetric encryption we use the same key for both encryption as well as decryption. So if you have plain text, which means the actual message that you want to do encryption, you use a key to do the encryption and use the same key to also do the decryption to get back the plain text. So the in between, the encrypted plain text is called the ciphertext. So these are some terminologies you should also remember. Now, in asymmetric encryption, you use two different keys. One key for encryption, other key for decryption, and of course they're related to each other. So we'll typically use an encryption technique called public key encryption to do asymmetric encryption. So in that sense, we have two keys called the public key and private key for each user. So if you encrypt a message with the public key of a user, you could decrypt the message only with the private key of the same user. Similarly, if you encrypt a message with the private key of a user, you could decrypt it only with the public key of the same user. So these are the two techniques in overall. Now what we are going to see is how we could use this encryption method to provide what is called confidentiality, integrity, and authentication. So as I also defined last time, confidentiality means we want to preserve the secrecy of the message. Integrity means we don't want the message to be changed during transmission. And authentication means the receiver should be able to verify that the message came from the intended sender or the sender who claimed to have sent it. Okay, so let us first see how to provide integrity and authentication. Now, you might have come across what is called hashing algorithms that could be used to generate, or even in the data structures class, if you have taken with me, you would have seen the hashing algorithms that could be used to generate what's called a hash value. So for a given message, you could generate a hash value of that message. So what's the purpose of this hash value? If you change your message, the hash value of the message would change as well. So with that you could decide whether, so if you send the message along with its hash value as part of your transmission, the receiver could recompute the hash value of the message it gets. And if the hash value of the message computed by the receiver is same as the hash value that comes along with the message, then it could imply that the message came without any change. If the hash value computed by the receiver on what it receives is different from the hash value attached to the message, then the receiver could conclude that the message got changed during transmission. So this provides you kind of integrity that the receiver is able to check whether the message got changed or not. Now we want to combine this along with authentication. So we want the receiver to be able to authenticate or verify that the message was really sent by the particular sender who the receiver thinks has sent it. So we need to use some way, some key that uniquely identifies the sender, and that will be the private key of the sender. So the idea is here you compute the hash value of the message you want to send. So indicate here the source side. So you compute the hash value of the message you want to send and then encrypt that hash value with the private key of the sender and send a message along with the encrypted hash value on the communication channel to the receiver. So when the receiver gets it, it will compute the hash value of the message, which is in plain text. It's not kind of encrypted. The message comes as it is. So there's no confidentiality. Anyone who's listening to the channel can see what the message is. So we are not designing this for confidentiality. So then the receiver could also decrypt the encrypted hash value using the public key of the sender, because the hash value was encrypted with the private key of the sender. So the receiver needs to use the public key of the sender to decrypt the hash value and get the actual hash value of the message. So the receiver will also compute the hash value of the message it gets, and if both the hash values match, it means the message came without any modification during transmission. If someone is listening to the channel and modifies the message, they cannot, of course, they can compute the hash value of the new message also, but they cannot encrypt that hash value with the private key of the sender, because only the sender knows its private key. Some third party person who is modifying the message cannot use the sender's private key to encrypt the hash value. So this is the way we provide authentication. So if the message was changed during transmission, so the hash value of the message would still remain the same as what the sender computed on the message the sender wanted to send, and they both will differ if the plain text message that comes along has got changed. So this way we can make sure the integrity of the message is preserved or not, as well as if somebody modifies it and uses their own private key. So you could think, why can't the attacker who modifies the message compute the hash value of the message as well as use his private key to encrypt the hash value? They could do it, but the receiver thinks the message came from the particular sender. So the receiver will always apply only the public key of the sender who he thinks has sent it. So one thing I might have told before, but you should remember that if you do not use the right key for decryption, both in symmetric as well as asymmetric encryption, what you get is like a garbage message that won't make any sense. So you have to use the right key for decryption in both public key encryption and symmetric encryption. So if the hash value was encrypted by the attacker using his private key, and the receiver uses some other user, which is the original sender's public key, the hash value again will come out something as a hash value, but that won't match with the hash value that the receiver will compute for the modified message. Even though the hash value that was encrypted will correspond to the modified message, when you do use a wrong key for decryption, what you get out of the decryption process will not be the same hash value as what it was encrypted. So the key that you use for decryption has to be the appropriate key, otherwise you won't get what was encrypted. So any question on this, you can use your microphone or type the message. Okay, so let us continue. So now what we want to use is provide confidentiality to the user. So here again we do not focus on integrity and authentication. We want to make sure the message that was transmitted by the sender is seen only by the receiver. Nobody else should see what the message is. So that is what we mean by confidentiality. So for that we could now, this is like generating a secret key dynamically. So that's a very commonly used idea, and it is considered to be very secure. So you don't maintain a secret key for a session. That could be also done, but a better technique would be to generate secret key for every message and send that secret key along with the message to the receiver, and only the receiver should be able to know what the secret key is and use that secret key to do the decryption and see what the message is. So of course a secret key you generate to encrypt the message that you want to send should be seen only by the receiver. So the idea would be to encrypt the secret key that you generate for that message with the public key of the receiver. So only the receiver could decrypt this with his private key. Nobody else should know the private key of the receiver. So when the receiver gets the message, gets the whole thing, the receiver will first decrypt the second portion and get the secret key that was used to encrypt this message. So then the receiver can apply the secret key and decrypt the message. So when I say secret key, it means like symmetric key encryption. So it's the same key that is used for both encryption and decryption. So this way you can provide confidentiality because nobody else will be able to decrypt and get the secret key other than the intended receiver. Now, does it provide integrated authentication? No, because anybody who knows the public key of the receiver can generate a secret key and encrypt a message and send that to the receiver. So, the receiver cannot make sure the message comes from a particular sender, or also even the integrity. The message could be modified, and of course, integrity and authentication go together typically. So, someone could generate a new message and send on their own, and the receiver could still process it. So, this does not provide integrity and authentication. So if you want all the three together, so the idea is to combine what we have seen so far. So to provide integrated authentication, we typically encrypt the hash value of the message with a key that is known only to the sender. In this case, use a private key of the sender. So to provide confidentiality, we encrypt the simple message with the secret key that is generated specifically for the message. So instead of the message, we can put here the message along with its encrypted hash value and encrypt the whole thing with a secret key generated for that specific communication. So that's the idea I am showing here. So you generate a secret key at the sender side that is supposed to be known only to, or that's supposed to be known only to the receiver. So you encrypt this with the public key of the receiver. So only the receiver could decrypt with this private key, and use that secret key to encrypt the message along with its encrypted hash value. And so you see two layers of encryption here. So first you encrypt the hash value of the message with the private key of the sender. So this kind of authenticates that the message comes from a particular sender, and encrypt the whole thing, which is the message and its encrypted hash value, with the secret key generated for that specific communication. So you could do that. You could have more than one layer of encryption, and then so when the decryption is done, you have to first do the outer level of decryption. So you have to first decrypt this message, the secret key, by getting the secret key from this part by using the private key of the receiver. And once you get the secret key, you can do this decryption and get the message along with its hash values. That's what I'm showing here. Once you do the decryption with the secret key, you can get the message along with its hash value, with its encrypted hash value. And then you decrypt the encrypted hash value with the public key of the sender, because it was encrypted with the private key of the sender. So once you do that, you can then compare the hash value that was sent along with the hash value that you would compute for the message the receiver side. If both of them are matching, then the message did not get changed during transmission, and it was also sent by the intended sender. And there's confidentiality because nobody else other than the receiver could process or see this whole thing, because it was encrypted the secret key that can be decrypted only with the private key of the receiver. So this way you can provide all the three things: confidentiality, integrity, and authentication. But as you can see, there's a lot of overhead with this. Instead of just sending the message, you need to send all these things: the hash value, the encrypted hash value of the message, and the secret key. So that's the kind of the trade-off. You have to send additional bytes of information in addition to the message bytes that you're sending. Any questions so far? So which diagram you're talking about?
Well, I guess it was really each of them, but
Okay.
it's really just learning about what these symbols mean, such as
Okay.
KS.
Yeah, so KS means secret key,
PUR.
PU means public key, and R means receiver, and
Right, okay.
PR means private key, again of the receiver. So I went through the process. I explained for this, but let me go through it one more time quickly. So to provide confidentiality, you generate a secret key, and that is this KS, and you encrypt that with the public key of the receiver, so that is shown here. So encryption, so EP means encryption, encrypt with the public key of the receiver, and also use that same secret key to encrypt that message. So that's what is shown here. So combine the encrypted message along with the encrypted secret key and send it. That's what this means. And at the receiver side, the receiver gets the whole thing that you're sending, and so the receiver should first decrypt the second portion, which is this, with his private key, because it was encrypted the public key of the receiver. So the receiver should decrypt this with his private key and extract the secret key that was used. So then use the extracted secret key to decrypt this portion, which is encrypted message, and get the message. Now for the third one, you first generate the secret key, which is shown here, the KS, and do the encryption. Okay, so generate the secret key and encrypt that with the public key of the receiver, that is this portion. Now you have to append with this, so before this you have to send this portion. So what you do is take the message, compute its hash value, first encrypt that with the private key of the sender. So concatenate the message along with this encrypted hash value, which is this portion, and use the secret key that you generated to do this outer layer of encryption, and concatenate that with the encrypted secret key with the public key of the receiver and send it for transmission. So on the receiver side, the receiver should be first able to extract the secret key in order to process this. So the receiver uses the private key of the receiver because it was encrypted with the public key of the receiver. So he decrypts with the private key of the receiver and it will extract the secret key and uses extracted secret key to decrypt this portion. So when you decrypt this with the secret key, you will get the message along with its encrypted hash value, which is this, and then use the public key of the sender to decrypt the encrypted hash value. And in the meantime, you can also compute the hash value of the message portion alone and compare the two hash values that you get. And if they are matching, that means the message came without modification. And since the hash value was encrypted with the private key of the sender, it also means that when you use the right public key of the intended sender, the hash values are matching. So that means the message was actually sent by the particular sender. So you provide authentication also. Okay, is that clear now?
Yeah, it's more clear.
Okay.
Thank you.
Okay, so let me stop for a second.